Okay, hello. Hi, everyone. Welcome to this talk, Smart Contract Families in Solidity. My name is Jan Gorzny. I'll be presenting on behalf of Casper Beck, who was initially supposed to be giving this talk, but couldn't make it due to some travel concerns. Nonetheless, I'm a co-author on this work, and so I'm happy to present this, although this delivery might be a little bit rusty because I didn't get quite the chance to practice that I normally would have. You might see the branding is not the company I work for. I work for Circuit. Casper and others who worked on this do work at Quantstamp, and so the branding might be a little off, might be a little jarring if you try to associate me with my current affiliation rather than this. But I didn't have time to remake the slides, so we're just going to roll with it, and we're going to talk about smart contract families. And so, what are we talking about? Well, smart contracts are software, and you can have a notion of software families. So if you're a one-off app developer, maybe this isn't something that you're super familiar with. But if you spend a lot of time in open source software, it might be a little bit more common because you have essentially a set of a code base which can be configured into multiple different versions of that, depending on what features you want included or custom modifications you want. So essentially, you have sort of a standard code base where you can configure some features and functionality, and then people fork it and build different things. Maybe some features get merged back and you want to use them in some deployments and not others. So some common examples of this include like the Linux kernel, right? The core kernel functionality is pretty standard across all distributions, but some distributions may come with by default some functionality that others may not. And similarly, stuff that is in a lot of hardware like cars. So you have a sort of a standard probably UI or UX for setting your car's maybe radio or even the performance functionality under the hood. But if you don't buy the performance package, maybe the functionality to go into sport mode isn't available or something like this. But other than that specific functionality, you have the same software experience more or less based on this common set of code base. So this is what software families are. This is well studied in software engineering academia and in practice. People build this so that they can maintain the core parts and make that improvements to that as soon as possible for all the good common stuff, but also gives people flexibility to change that version for what they need. And no surprise that we're starting to see something like this in a lot of Solidity-based applications, right? This is not 10 years ago or 8 years ago, or whenever Solidity started to become sort of popular or prominent on Ethereum. We've matured as an ecosystem, and there's a lot of similar but different pieces of code out there. And so I think it's time that we start talking about a lot of this as a smart contract family. So if you're building a dApp, actually start to think about what it means to have a single version that you might want to redeploy on multiple networks or in multiple different contexts. And ideally, you don't want to do this, but the reality is this is something that's pretty valuable and often overlooked and not discussed, right? So there's a lot of chains out there that will say, you're EVM compatible or EVM equivalent, and so you take your code and you want to actually do it on the same, use the same code for multiple different versions of the network, which is not ideal. Obviously, we'd all love if there was a single, liquidity source or single implementation of a tool, just so it's simpler and easier to maintain, and you don't have to worry about liquidity fragmentation. But the reality is that's probably not the case right now. In a lot of situations, you take the same code, you fork it, you put it on your specific network, you get your users there, and then you might have different users using a slightly different version of the chain on a different one, and that's life. So maybe if we get new tech, new interop, this will disappear, but I don't think that'll be truly the case ever. I think there's always going to be a reason why you want to do something on different chains. And so in this case, it might be very clear that you'd have multiple rollups. There's like 100 in development according to L2Beat right now, so there's a ton of rollups, and most of them say they're EVM compatible. Not all of them. Some of them by design. Others less so. And actually, it's not clear that they're exactly EVM compatible, or sorry, not EVM equivalent. Most of them are compatible, but there's actually a lot of really subtle changes. And so if you actually take a look at under the hood at the EVM implementations of these rollups, often they will change slight behavior. Not major changes for the most part, but you might start to see that some things do different things on different blockchains. So some rollups will, for example, change the operation or change the result of calling, the block timestamp. It might give you the L1 timestamp for that L2 epoch, or it might give you a time tracked by the L2, or you might support specific features that either are ahead of or behind rollups. So you might really want revert. Maybe your rollup doesn't implement that because Ethereum sort of wants to deprecate it. And so maybe they've gone ahead and done that on their version of the network. Nonetheless, this means if you want to have an exactly equivalent situation for your code base, it's very, very difficult. You either have to restrict yourself to some very specific situations and chains where you can guarantee that this is the case, or you have to deal with it. And maybe your app just doesn't care about it, in which case it's also pretty easy. But the actual feature set that changes from chain to chain is maybe not well defined, and you have to go investigate and you have to figure it out for yourself. So if you can build all of this with a software software family in mind, maybe we can make this simpler. So let's see how we can do that. And there are a couple ways we can do that. But first, let's define the goals. So what do we want? We want to be able to develop, manage, and deploy similar products across chains. So ideally not too different among different chains, but we want to be sort of having a core common code base where we can change specific parts that relate to the specific chain we care about. And what we also want is a really large common code base if we can, because we want to reduce the costs of audit. A lot of smart contracts obviously get audited so that other people can take a look at the security issues, and hopefully there are none, but if there are any, they fix them, and then they go to deploy. And so you want to reduce all of this, because you don't want to be saying, okay, I had a version on Optimism, I got it audited. I have a different version on Circuit, yeah, I got it audited. What you want to say is, I have one nice thing that's audited, and maybe I changed a line or two, and maybe you still need a diff audit for that. Probably you should, but you don't need to say it's totally different. You don't need to start from scratch to an auditor. You can say, look, I have just this part changed. Ideally, if you can actually give them the whole family at once and say, look, these are the different versions that I plan to compile into, or otherwise use, there's a need to only get one audit maybe, and that's kind of nice because the audits can be expensive. So let's go into some specifics with an example. And here my example will be that of a retirable contract. So something we can retire, basically we want to stop using it at some point. And now if we look at this contract, it's a very small contract. It takes some stuff, it has some money, that's the important part. And then maybe at some point you want to retire it. You don't want to maintain it anymore, or you want your users to upgrade. I don't know, you have an excuse that you've convinced yourself it's worthwhile, and you don't want this contract on chain anymore. So you have this thing, so let's retire, you force this function, or this thing to be retired. Probably this should not allow anyone to be calling it. No, perfect, it's got a message sender guard, that's good, and you have implemented using it as self-destruct. Okay, so what's this gonna do? Well, on Ethereum it's deprecated, so that's not good. In other places, it might revert only. Is that good? Is that good enough? I don't know. Maybe your funds will be trapped in there, right? You want self-destruct in the old behavior, at least it would self-destruct and send the money somewhere. If it just reverts, maybe the money's trapped there, or maybe that reason that you originally had to ensure that this contract is retired actually disappears, and that's not good either. Or in other situations, maybe it just won't compile, right? If this is long enough and the Solidity library has moved on, this is no longer valid code. And so when you go to redeploy this on a modern chain with a modern compiler, maybe it doesn't do what you want. So this is annoying, right? We want to see if we can fix this. How can we fix this? Well, there's a couple ways we can do. We can do what we call clone and own. So this is the idea that you take a smart contract from somewhere else that exists, you clone it, copy it, make a copy, git fork, whatever you want to do. And then you make it your own. You put it in your own repo. That's the own part. And then you change it because it's yours. You can do whatever you want with it now, right? Subject to licensing and all that. But like you essentially have your own version of the code that now you have to maintain separately from the original version. And then what you do is you change, okay, if I know this call is going to be problematic on some chain, I'll replace it with a call that's more friendly. In this case, a receiver.transfer. And it'll do that. So sure, we can do that. This is probably the most straightforward one. This is probably the one that everyone will think about if they're not sort of familiar with other options, or if they're doing it quick. In a lot of cases, even we saw other projects that weren't necessarily optimizing for development time still do this because they just want their own copy of the code. But there's other ways you can do it. You could build for this, right? At the very beginning, you can say, I know that this line of code is going to be a problem, but I'm not too concerned about the size of my contract. I'll talk about the downsides of these approaches later. And if it's on Ethereum, so if I have a specific chain ID, I'll do this behavior in the contract. And if I have a different behavior or a different chain ID, I will do a different behavior. And so in this case, we fork on where we are deployed with this contract execution, and it does the appropriate thing that we think it should do. And that's also neat, but kind of a mess to start reading your code. You start looking at this contract, now you got to figure out multiple paths at once. If you're a security auditor, not exactly the most convenient thing to do. You're always trying to keep a mental model of what the system should be doing. And if you have these everywhere in your code, it's going to be really chaotic to figure it out. So you're going to have to consider it in different chains, and there might be nested ones. I don't know, right? It could be a lot of stuff that goes crazy. What I think is the best option, though it's the perhaps the biggest engineering lift, is what we call conditional compilation. This is a little bit more akin to traditional software families. This is why I'm talking about this. What we can do is actually specify different sources for parts of our code base at a given time. And then at compilation, we say, I'm going to compile with these features enabled, or for this chain, or for whatever the flags are. And what happens is you build the common core out the way you want, and you put in some sort of indication as to where the specific functionality that will be changed depending on the compilation options. And then when you go to compile, you specify the flags and everything works. And so that's what we wanted to do. In this work, we were just trying to see if we could do that with ease, because what I just described to you actually doesn't sound that hard, but if it takes 3 hours or 3 days to do, no one's going to do this. So we wanted to see if we could do it in 20 minutes or something short, something convenient developer experience-wise. And that's what we talk about. And so here's an example here of that motivating example with a conditional compilation. You see it's still kind of an annoyance to read, to be totally honest. That part's probably not optimized entirely. But when you do get a compilation that's complete, given the specific flags, that version is very easy to read. So now, when you're trying to understand the behavior of this contract on a specific chain, you can remove all of the considerations for other chains in this example. And so on the left, we would indicate that in this retire function, we have this area where if your compilation flag is set to mainnet, do this line of code, otherwise do something else. And then you take an extra step before you compile using a macro and some pre-processing stuff that actually exists. We repurposed a lot of the stuff from the Linux library, I believe, for this work. And when you hit the compile with those flags, you do get just one version of that function, which is very nice. So now if you're an auditor, you can say, okay, I got to look at this code. That's great. I'll compile it. But also tell me what chain you're on, and now I don't need to worry about the rest. And hopefully, if you're a good auditor, you also do the other ones if there's time and you think there's a concern. But at least for the version you were supposed to do, you can figure it out very easily, which I think is really, really nice. Okay, and so how do we actually do that? We do that with a C preprocessor. C is not something you probably hear too much at an Ethereum CC conference, but yeah, they have that. That syntax looked like C. There's a reason that was the case. The C preprocessor that was used here, I think, was the one, like I said, that I already mentioned, I think was used for the Linux compiler, kernel compiler itself. So this is, not some script that could break. I mean, obviously it could break, but it's one that's mature and battle tested, and it does this job very, very well. So then you start writing these macros in your Solidity contract, which then stops being sort of pure functional Solidity in the sense that the compiler will complain if you skip this step. But if you don't skip this step, you do get the option to use this using sort of top tier battle-tested scripts for compilation, and it's very easy to specify. There's a bunch of little flags there that I don't know off the top of my head. I'm not the only author for a reason, and you get the code that you want, which is really, really cool. And then you can also, do this programmatically. So those flags, like I said, really annoying. But if you have a really large software family or you have a lot of configuration options, you can do this using, some sort of a config file where you can specify different versions of this across different things. And all of this will be picked up by the script. And at the end of the day, you'll get something that's, Solidity that will work on your EVM compatible chain. And also, you can say you borrowed ideas from some really good software engineering stuff. And it does scale. So it was a scientific paper, so we had to at least justify, is this approach going to be viable or useful? I don't have a lot of stats on this, unfortunately. It's not my slide deck. But this works for hundreds of features for the Linux kernel. It's definitely going to work for your little Solidity contract, which generally speaking are much, much smaller than things like the Linux kernel. So it works well. We provide scripts to do this, basically just the stuff you need to get it done. So I don't know if actually there's a link to the specific GitHub repo, but if not, come ask me. I can definitely find it for you, or look up the paper, and we can definitely do it. And then once you have the scripts and all the compilation options are done, you just compile Solidity the way you want. In this case, we use Hardhat, and it works. Okay, so all I've been trying to argue is that maybe there's a situation where you want to do slightly different versions of your Solidity for slightly different things. Might be different chains, might be different use cases. You don't actually have to restrict it to only modifying behaviors of dangerous opcodes. You can be totally different in your feature set, of course. Right? You can say on one chain, do something, or in one deployment, do something. In a different deployment, do something entirely different. You could have the function not retire, for example. We could send money somewhere else, or upgrade it, whatever. Anyways. there's a lot of things you can do with the smart contract families, but to sum up, this is the comparison of these approaches, right? If you're looking for bytecode optimization, clone and own will work, but then you're dealing with multiple versions at once. Just as effective to use this this conditional compilation method, because at the end of the day, what you put onto a chain is optimized by the compiler without additional conditionals. So that's nice, because obviously when you compile, you don't specify what chain it is generally. And so that's also true of execution cost and compilation cost. I guess there's one extra pre-processing step, so maybe there's a thumb up with a little asterisk over there, but still pretty good. And you're still going to get the standard compile time errors for any specific version you get. So as a developer, it's still pretty good. The clone and own is a little harder for the auditing team themselves if they want to do something like this, because they have to go figure out if there's any version of the code that contains bugs that you didn't clone, right? You might have cloned a version that was pre-bug fix, and that's a problem. In this case, you get to see everything all at once, so I think it is a little bit nicer. I will say I would maybe have put this as a slightly different symbol, because again, if you have to do multiple versions of it, maybe the auditing is not the best, but it's still pretty nice. And certainly the conditional compilation has very good readability, right? So you're only looking at the single version if you want, but also you can look at different versions, and you can consider them in different ways, but that's probably unavoidable. If you have different versions of code, you have to look at different versions to understand what they're doing differently, right? So that makes sense. The downside is with this approach, because although we use some great stuff from the Linux Foundation, all of that, I don't think there's any testing and tooling around, that supporting the different versions at once and testing each possible configuration, of which there may be many if you have a lot of features. But if you're interested in this and you think there's a good use case, or I, just convinced you that this is a valuable approach, build it. Go build it into, your favorite testing framework, and they'll probably be happy, and you'll be happy, and everyone will be happy. So that's basically it. That's what we did. I hope you found it, informative, and maybe you'll consider using it. We do have code available. I guess it's not linked here. But essentially, if you're going to do multiple things, clone don't work sometimes, but if you're really deploying a lot of versions, mix it up, do something better. A lot of better software engineering has existed over the last 30 years, 50 years, not just the past 4, 5, 8 years of Solidity. Learn from it, do something better. And in this case, we showed that you can actually do conditional compilation if that is what you want. And it's very valuable, it's very quick, it's very easy. So that's it. That's my last slide. So thank you. Do I have time for questions? Yeah. I do have time for questions. I have 2 minutes. Okay. No questions, and I'm okay to be done. Thank you.